Hi, this is Tim Ojo presenting my graduate project, CNV Research Web Application. The objective of the project was to develop a web-based application to implement the research paper by Yi Zhang, Dr. Hong Chin, and Dr. Li Yang, called Identification of Health Disparity Associated Copy Number Variations through Network Analysis. The intent of the project was to provide a web interface through which the network analysis that was prescribed in the research paper can be done in an automated, publicly accessible, and user-friendly manner. The objective of the research paper was to analyze whether frequency variations between copy number variations, which are going to abbreviate as CNV, in African Americans and Caucasians allow us to infer potential diseases and health disparities in the two aforementioned populations. In order to achieve this, we have to follow the following steps. First is to infer network clusters from human gene networks using the MCL algorithm. After that's done, each network cluster must be evaluated for the occurrences of known pathogenic genes and the CNV genes using Fisher's exact test. And then all the clusters are ranked by their p-values to determine which clusters are considered interesting or not. After interesting clusters are identified, geoterm and phenome type analysis is completed on these clusters using online search tools called Gorilla Search and the OMIM database. This web application is designed to complete the cluster analysis phase with the steps mentioned in front of you and provide links to Gorilla Search and the OMIM database. It implements all the analysis algorithms and methods used in the paper and puts them in a simple application workflow that's accessible to everyone and can be used very easily. So now let's take a look at the project requirements and deliverables. The first project requirement was to create a welcome page that would introduce the research and its authors. The second project requirement was to provide a gene networks page that would allow users to upload their gene networks for MCL clustering or to upload their already clustered networks, which will go through a validation process. Validation will be used to check whether the gene network files that they upload are really text files and whether they conform to the format that we're looking for. And the format that we're looking for is that each line should be a pair of genes separated by tabs. For gene cluster files, we also validate them to make sure that they are text files, and in this situation each line will be a set of genes separated by tabs. For the MCL clustering in the gene networks page, we also provide the inflation parameter, which can be specified by the user or defaulted by the application. The third project requirement was the provide CNV select page, which would allow users to upload the gene names to be used in the cluster analysis or to search the UCSC database for the gene names. The initial requirement was that the user uploads 3 sets of genes for use in the significance tests: OMIM, CNV gene set for Caucasian Americans, and CNV gene set for African Americans. But that requirement was later modified to state that the OMIM gene set is required, as well as either one or both of the CNV Caucasian American and CNV African American gene sets. This allows us flexibility where we can analyze both gene sets at the same time or just one of the gene sets at the same time, that is CNV Caucasian American or CNV African American gene sets. fourth requirement was to provide a database search page to allow a user query the UCSC MySQL genome database for either gene names or for chromosomes and their coordinates on the chromosomes. The database search page should be able to use as a standalone feature or as part of the overall research. When used in the research, there are certain steps we want to take. For example, we want to remove duplicate genes, and we also wanted to remove genes that are not in the gene network that is currently being analyzed in the app. The next requirement is to provide a begin cluster analysis page to kick off the cluster analysis process. This page will be responsible for checking to make sure that the inputs are available and properly formatted. Also, for each gene in every gene set uploaded, we are to assign that gene a cluster label to indicate what cluster it belongs to, whether CNVAA or CNVCA. And then we kick off Fisher's exact tests with the provided inputs. The next requirement after that is to provide a cluster analysis results page to display the results of the cluster analysis, that is Fisher's exact test. In the results, we want each row to contain the info for each cluster, such as cluster sequence number, gene numbers, and p-values. However, not all the results will be considered interesting, as some of the results will have p-values as high as 1 to show that no processing was done. Therefore, we only want to display results that meet certain criteria. The default criteria is that the OMIM p-value, or the pathogenic p-value, would be at or below 0.05, and the gene set p-value for either CNV African American or CNV Caucasian American would be at or below 0.1. These are the default values. However, we wanted to give users the ability to change the p-value thresholds for both the pathogenic genes and the CNV gene sets, giving them the control of deciding what gene sets, what clusters are interesting to them or not, so that then they can do further research on those clusters as they see fit. The next requirement is to provide a cluster details page to enable further analysis of that selected cluster. The cluster details page would include the cluster sequence number, the names and the counts of all the genes in the cluster, the names and the counts of the OMIM genes, and the names and the counts of the CNV African American or CNV Caucasian American genes. And so here we have a diagram of the workflow that we alluded to. The workflow starts with the welcome page, goes to the gene networks page. To allow you upload the gene network, goes to the select CNV page to allow you upload or select the CNV gene sets as well as the pathogenic gene sets. However, what we're looking for is the names or the symbols of the genes within that gene set. However, and if you do not have that, you could go search the UCSC. As you can see here, you could go to the UCSC search page to search for that information, and then that information gets returned to the begin cluster analysis page. Or if you have it, you could go directly from the select CNV page to the begin cluster analysis page. The begin cluster analysis kicks off Fisher's exact test, which produces the results, which end up in the cluster analysis results page, and then the cluster details shows further details on a particularly selected cluster. This was the original workflow. The project deliverables are a tested and approved Java web application project that can be deployed in Tomcat or in any Java EE web container. Another deliverable is the project demo or presentation, which you're now listening to, as well as the final project report. Additional artifacts that I will be delivering are user documentation, which shows users how to use the application. This user documentation is also available within the application that is deployed on the references page. Additionally, I'll be providing instructions on how to deploy the application, technical instructions, as well as source code to allow for further development and maintenance of the application, which there is potential for further development in order to improve upon the algorithms as well as upon the usability of the application. So let's take a look at the project design. There are two primary ways of developing web applications today. The first that we're going to take a look at is to have separate front-end and back-end projects. The front-end project will be purely HTML5 and JavaScript, the purely UI, and the back-end project will be written in a language of your choice and exposed as RESTful web services. And the front ends and the back ends will communicate over the HTTP or HTTPS protocol, and the user would have to perform all the functions necessary to make the web application perform to their liking. The second way of developing web applications is to develop using a web application framework such as ASP.NET MVC, Django, which is Python, Struts, and Spring MVC, which are Java web frameworks, and Ruby on Rails, which is obviously Ruby. These are just examples of the multitudes of web application frameworks that exist today, that all each have their purposes, their uses, and their advantages and disadvantages depending on the language that you're working in. The benefits that web application frameworks provide are things such as session management, dynamic templating, code reuse, etc. In particular, I was interested in session management because the project has some state data that needed to be maintained as it crossed through lots of different HTML pages. And so I chose to use Java Server Faces 2.x framework. Some of the reasons for this were the need to integrate code already written in Java by Yijang, as well as the large support system for Java development at UTC and in the Programmer Society at large. Because if this project was to be further maintained at UTC, it would be better for it to be in Java and not in a language such as Python or Ruby. Other reasons to choose JSF is that JSF offers the advantage of having very good performance, good scalability, decent ease of use, and it is championed by the Java EE standards community today as their proposed way to develop web applications. Once a web application framework is chosen, the design of your application within that framework is then guided by the paradigms that are established by the framework. As we chose Java Server Faces 2.x, the primary components of Java Server Faces become our primary components. The primary components of Java Server Faces are JSP pages or facelets. These define the views that will be rendered on a user's browser or device. Java Server Pages facelets provide support for CSS and for JavaScript, as well as simplifying AJAX calls and dynamic navigation. Java Server Pages 2.x are dynamic and also backed by managed beans. Let's talk about managed beans for a second. What are managed beans? Managed beans are plain old Java objects, POJOs, which are annotated and maintained by the container. The container maintains their state and maintains the session on your behalf. The managed beans typically provide the business logic of the application, and so that's where all your calculations would go. The views for this project were written as JSF and HTML pages. I have one managed bean, the research session managed bean, that's responsible for maintaining the state variables. That's the data on behalf of the user. That's responsible for dynamic navigation based on that state, and also responsible for delegating calls to specialized classes, which would then perform the research functions such as the MCL clustering, the UCSC genome database calls, and Fisher's exact test. The decision was made to maintain the state data in memory instead of in intermediate files for performance and convenience reasons. Essentially, instead of at each stage of the application writing to a file and then reading from the file at the next stage of the applications, I chose to maintain the state data in memory because performance of I/O is much slower than performance of data access in memory. In addition, it was much more convenient to maintain it in memory, and the biggest file was less than 300 kilobytes, so that is not much memory to be taking up, especially in a powerful web server. Before I get off the design, I needed to note that in the design phase, the decision was made to merge some of the views originally laid out in the requirements phase for reasons of streamlining and for reasons of aesthetics. Essentially, if each of the phases, each of the life cycle had been a page in itself, there would be enormous amounts of white space, wasted white space, and not much functionality, and the user would have to do way too many clicks just to get through the application. By streamlining it, you make better use of white space, you provide a better looking web application, and you save the user clicks. All the functionality was maintained. However, we just moved the views around a little bit and merged some views together while maintaining all the functionality of the workflow. So the workflow is intact, but it looks better now. And here is the architecture design of the project. It is a 3-tiered architecture. The first tier is the UI tier that has the HTML and the XHTML pages, welcome app, UCSC DB cluster results, and references. These communicate through the research session into the middle tier. The middle tier provides the business logic. And as I mentioned earlier, this research session .java maintains the state and does dynamic navigation based on the state, and also delegates calls to specialized classes that would then perform the heavy lifting. Those specialized classes are cluster MCL.java, UCSC genome DB.java, and Fisher's exact test.java. And you can summarize from the names. They're pretty descriptive what each of those specialized classes do. The cluster MCL.java communicates with what I call the third tier, the platform tier. It communicates the MCL software on the platform to provide the MCL clustering. The genome UCSC db.java class communicates with the remote MySQL database at the UCSC site for the translation from chromosomes to gene names and vice versa. Fisher's exact test communicates with the R statistical software installed on the server to provide the network cluster analysis functions that we are working with. Therefore, you have the three-tiered architecture that is presented to you here. After the design phase comes the project implementation phase. Development was accomplished in a little over a month between the 15th of June and the 18th of July. Over 3,100 lines of Java, HTML, JavaScript, and CSS code was written for this application from scratch. And within the project implementation, there were some lessons learned and some new ways of doing things that will be discussed in the lessons learned slides that will come later on. But first, let's talk about the project results. For the project results, it must be stated that all the objectives mentioned in the statement of intent and in the requirements gathering phase were accomplished successfully. The web application code was completed on the 18th of July, and it was hosted onto a web application server in EMCS Lab 323 on the 27th of July. It's accessible at utclab.ddns.net/cmv_research. The application has also been tested and approved by Yi Jiang and Dr. Han Chen, and forgive me for the PowerPoint getting cut off at the bottom there. So let's do a quick demo of the web application. And so here's my desktop screen. I just switched to it, and here's the welcome page. It's available at utclab.ddns.net/cmvresearch/welcome.html, or you can just go CMV Research and it'll automatically link you to the welcome.html page. The welcome.html page has some introductory text taken from the paper, and it also introduces the research authors, Yi Jiang, Dr. Han Chen, and Dr. Li Yang. There's a start button that would then take you to the applications page, or you can directly go to the applications by clicking on the tab up here. So I will click on the tab up here to show you the applications page briefly. There's also the UCSC database page right here, and then there's the references page right here. As I mentioned earlier, the references page has a user's guide that would show you how to use this application. Clicking on it gives me a PDF that I created that's opened in a new tab. It gives you detailed instructions with screenshots on how to use the application. But instead of taking a look at that, let's take a look at the application itself. So we're going to go back to the welcome page, and we're going to click Start. As I mentioned, Start brings us to the application page. Here, step 1 is the gene networks page. Essentially, we upload the gene networks or upload clusters. It has some introductory text as to what kind of files we're expecting. Also, it tells you where you can go download gene networks at the Human Protein Reference Database website. We've done that already, downloaded some gene networks from the Human Protein Reference Database's website, and stripped out all the excess information, sans the two interacting proteins, and we've made that available here. So here you can download some sample files for the gene networks from HPRD, and you can see the gene network here, which is a pair of interacting genes. And you can see that this file is called ppin_0.txt. It can easily be downloaded if you right click and say save as, and it'll download for you ppin_0.txt. But that's done for me already. I don't need to do that, so I'm going to close that. I'm going to close this, just showing you the sample data that we have here of the gene networks. We also have sample data for an already clustered gene network file, and you can see that right here. And this is also a txt file that you can download. And so these are sample files that are available. But in the first phase, the primary task is to either upload a gene network or upload a gene cluster file. You do so by selecting choose file. Choose file brings up a file picker application, and you can come in here and select your gene network file. I'm not going to do that for time's sake. Instead, I'm going to upload a gene cluster. And the reason I say for time's sake is because the clustering phase takes roughly 2 to 3 minutes, and so instead of wasting your time, I'm going to upload a file that's already been clustered by MCL algorithm. One thing to note is here we have the MCL inflation value, and it's defaulted to 1.4, and it can be changed to 2 or 1.5 or whatever you want, but it's defaulted to 1.4. This is flexibility that we allow the user to have. Okay, so as I said, I'm going to upload a gene cluster file. I start by clicking choose file, go to documents, and select my cluster file, and then I have to click upload to complete the actual upload. And once that's done, a green checkbox check mark shows up right here to show me that the upload was done successfully. Phase 2 of the workflow is to upload the list of genes to analyze. Here the genes can be labeled to your liking, so I'm going to label this one CMV_AA. I'm going to choose a file, and upload it. I'm going to label this CNV_CA. I'm going to choose another file and upload it as well. And you can see the green check mark always appears. If you don't have sample data, again, sample data is available here. Both these files that I used are right here available as sample data. If you click on it, it opens in a new tab. And like I said earlier, you can save as, and it'll save the sample data for you. It's a convenience that we offer. The last phase before all the files are gathered is to upload a list of pathogenic genes. So I'm going to come here, choose file here, and say upload. Now I can choose to reset the form if there's something that's not to my liking, or I can click next, which is what I'm going to do. And next is going to click off the cluster analysis using Fisher's exact test. It takes not very long. because there was already a clustered, we already uploaded a gene cluster file instead of a network file that would have to be clustered. If it was a network file that would have to be clustered, it would take significantly longer time. But here's our cluster analysis results page. And as I mentioned, you can adjust the pathogenic p-value and the gene set p-value to increase or decrease the threshold as you see fit. So if I were to reduce the reduce the gene set p-value to say 0.05, here I have no results. Here I've got 4 results. Here I've got more results. So I'm going to go back to defaults. I'll see the results, and the results are the cluster number, the number of genes in the cluster, the number of pathogenic genes in the cluster, the number of CNVAA genes, and the number of CNVCA genes. These use the labels that we passed in earlier. So if we had named this CNVCA and this CNVAA, or CNV doohickey and CNV something else, it would be CNV doohickey and CNV something else. The pathogenic p-values, and then the gene set p-values for whichever gene set it belongs to. There's other resources here that you can click on: OMIM, Princeton Geo Tools, and the Yeastmine genome database, as well as the Gorilla and the, again, Princeton Geoterm Finder tools that are provided here as links for further research after you have your cluster results. But we also can show a few more cluster details. If you click on the link, which is a cluster number, it'll tell you the cluster you're looking at, and it'll list to you all the genes in that cluster. It'll also list to you the CNVAA genes in the cluster, as well as the pathogenic genes in the cluster. And again, we're using the labels that were specified in the previous page. If you click on this, it changes that, and these are AJAX calls, so you notice that the whole page doesn't refresh, just this portion of the page refreshes. And so here we have the genes in the cluster. There's 9 of them, and the pathogenic genes in the cluster, and the CNVCA genes in the cluster. And this is designed this way instead of as a table form, so that you can easily select the list of genes and possibly use them in Gorilla Search, or in other search tools. I'm not going to do this here, but you get an idea of how this is useful, having them in this format. So I'm going to go back to the applications page, and I'm going to click reset form so that I can show you a cool feature that was developed. And this cool feature is the search functionality. So let's say you have chromosomes and chromosome locations, and you want to find the gene names that are within that location. You can click the search button, and here I'm going to paste in a list of chromosomes and chromosome locations. So for example, this is chromosome 2 at location 88,922,304 to 89,912,849. I have to select my query type. So my query type here is chromosomal positions to genes. I'm going to click process query. It goes and searches the UCSC database, the UCSC genome database, University of California, Santa Cruz genome database, which again we always provide links to our references here, so that's the link to the database. And here are the genes, the gene name, the gene symbol, the chromosome, chromosome start, chromosome end, that are found at that location. And so what's cool about this is if I click finish, because I clicked from the search link, it's going to take me back to the search link and upload that list that I had in the UCSC database into my results right here. So that's a great feature that we have. To further show you an example, if I click choose file and then click CMV input, and here is a file that contains both CMVAA and CMVCA genes, and I have this checkbox that is customized especially for this particular type of research, that would then allow us to be able to separate both gene sets into two different files. So I'm going to go ahead and click upload to upload it, and I'm going to click process query. And this is a large file, so the search takes a little longer. As you can see, the search returns after a while, not too long though. Again, with a list of gene symbols, gene names, chromosomes, chromosome start, chromosome end. What's different, however, is because this is checked, we also determine based on the frequency values whether this gene symbol is CMVAA or CMVCA, as you can see. Some CMVA and CMVCA. And now in this situation, if we click finish, we automatically upload CMVAA and CMVCA in here into your results for you to search. And since I've already done the search, I'm not going to do the search again. I'm just going to go ahead and reset the form. So you've also happened to see the UCSC genome database page as well. Then this page allows you either upload a file or enter the file, and then you can select the query type and click process query. One thing that you may not have noticed that we do is, if your file contains chromosome locations, for example CMV input, we will automatically detect what your file contains and change the query type on your behalf. So right now the query type is ID to genes. It detects that what you have in there in that file is chromosomal positions, and it changes it, the query type, to chromosomal positions to genes for you. Now this only happens with the file upload, but not with the entered query data. So I'm going to reset the form, and so now I've shown you the welcome page, the application page, the UCSC database page. I've also shown you the reference page briefly, and I showed you the results page. The reference page contains references, paper references, as well as software references. and I hope this demo is satisfactory. So let's get back to the presentation. I do have some lessons learned from the project. The initial challenges I had was a lack of understanding of the field of genetics and its vocabulary, and as a result of working on this project, my knowledge in that area is vastly improved. The second challenge I had was a lack of experience with the Java Server Faces framework. My prior web application development was done in PHP, and I also had some Java web application development, but that was in servlets and JSPs. However, the Java EE standards community is now actively pushing JSF as a replacement for Java for servlets and JSPs, so I had to learn JSF, and I had to learn on the fly. The book Core JSF was instrumental in getting me up to speed working on JSF, and now I consider myself to be at least a competent JSF developer. I did have challenges as well during development. One of them was the Eclipse Apache Tomee integration. Apache Tomee is simply Tomcat with a number of added jars to turn Tomcat into a fully fledged Java EE web container. Unfortunately, getting Eclipse to integrate with Tomee did not work properly. The reason was that Eclipse creates its own instance of Tomcat without the addition of Tomee jars, and so instead of descending into class path hell, I decided it was a better choice and a more supported option to revert to using plain old Apache Tomcat and include the JSF2 jars within the project's webinf/lib folder. I also had issues with debugging JavaScript. I had experienced some JavaScript errors, but there was no way of pinpointing what the issue was, what the error was, and where within JavaScript it was occurring. Luckily, I stumbled upon Firefox's developer tools, which included a debugger, a web console, and an inspector, and this helped me solve my JavaScript issues. The final issue that I had was in enabling the Java R integration. While some documentation does exist for enabling Java R documentation within a command line application, there was absolutely no documentation anywhere online for web applications that used the Java R integration. So it took me several days and several different trials to find the right placement of the necessary environment variables, shared libraries, jars, etc. to get the integration working. After the development was completed on July 18th, I went into a struggle with the network setup for the EMCS lab. It had been set up incorrectly, and so there was a lot of work to get the network set up in the EMCS to be able to access the web server from outside. Because a router had been set up, we could access it from inside the local network, but not from outside the local network. And so that was resolved, and now we have access, and we also have dynamic DNS working. And so those are the lessons learned, and in summary, I have to say that this project was a great learning experience, and it produced what I would consider to be a very good product that I hope will be further developed and used in the future. It involved several aspects from classes taken at UTC, which includes data structures, security, and networking. I'd like to thank Dr. Lee Yang and everyone involved, especially Yi Jiang, in helping. And so I will take questions at my email address, since this was pre-recorded, and thank you very much.